Okay, we're going to continue on from where we left off on the last lecture, but we're going to talk about the law of sines. And as I said before, it's A over the sine of A, side B over the sine of angle B, C over the sine of angle C. Now remember, none of these are right triangles, so this one is going to be a little odd. Let's see if I can draw you one here. We'll do that. We're going to put it like so. And it's going to wind up like so. None of these have a 90-degree angle in them, okay? We have A over here, we have C there, and B, this becomes little c for the hypotenuse. This becomes A, and little lowercase b, okay? And we'll go play with an example here in a minute, but I want to get you through all this. As we talked earlier, it needs to have, I need to have an angle and two sides, or I need to have two sides and, an angle and two sides, or two angles and a side, okay? So I can manipulate any of those any way I want, and that's how we're going to do this. So let's take an example, and this is one that Mr. Blickwadell liked, and we're going to use the same one again. It's an example of using geometric techniques to find, or trigonometry, to find a buoy out in some water, okay? So we have your two Okay, so it's a very general statement. We'll get a little more specific as I draw the details here in a minute. But location of an offshore point with two transits at an opposite end of a measured baseline. Okay, and we're going to take a look at this as here's our baseline, okay, and we're going to call that x equals 0 just to give us a reference to this, and then 90 degrees up from that we will take y equals 0. Out in the field, you're not going to have an x or a y, but you will have stuff related to that. Okay. Now, here's what we're going to do. I'm going to do a little creative here. We're going to use some different colors, but we're going to have a shoreline that does this kind of thing. Okay. And out here we're going to have water. Actually, as long as I have color, let's go play with it. We're going to add a little bit of waves. Okay, and we need to go back and figure out what we're doing. So out here, we're going to put in this location, and we're going to call this point C, but we're going to locate a buoy. Okay, and with that buoy, we're going to come off point A. All right, this becomes point A, and then we're going to have a point B. That's going to be way over here someplace. Oops, I don't want to drag the ruler. I want to draw along the ruler, and we're going to be like so. Okay, and this will be point B. Okay, but we have a known distance on our baseline here. All right, yeah, I should label that too. X equals 0 is our baseline, which we actually measured. So we're going to call this one 243.69 feet. Okay. And we have a angle in here, and we have an angle in here. Okay. A couple things to point out here is currently we're not doing this in our surveying class, but it is something that you can do later in the semester when we get a transit out or a total station. But we need to be able to measure angles directly. All right, so I'm going to give this one. Let me take a second here. I got to get the mouse off my angle measurement. Oops, too far. This one will be 32 degrees, 24 minutes, and 30 seconds. Okay, and that'll be angle B. Angle A, I'm going to take that one out around here, and we're going to give this one a measurement of 35 degrees, 46 minutes, and 0 seconds. Okay, so we now have two angles and a side. Okay, and this side right here is C is equal to the 243.69. Okay. All right, now for the math. Let's slide my ruler up out of the way. We're going to need that later, but let's do the math. Okay. So we know B, and we know side C, and we can find angle C. Okay, so that seems to be an easy way to get at this. Okay. And then the other bit is we know because it's a triangle that all the interior angles are going to be 180 degrees. So first step is let's find what this angle is up in here, and then we can truly find out what side B is, and then we can figure out side A. Okay, so first step, and I'm going to label this 1, is find missing, that's missing angle of C. Okay, so we're going to start out with 180 degrees, but I want you to remember that that is equal to the triangle having 179 degrees, 59 minutes, and 60 seconds. Okay, just save us from having to do some borrowing later on. Okay, now we know A is, let's do this a little differently. Angle A is a minus, because we're going to subtract it, 35 degrees, 46 minutes, 0 seconds. And we know that angle B will be subtracted from the 179, 59, 60. And that one's 32 degrees, 24 minutes, 30 seconds. Okay, and if we do the math for that, that's going to turn out to give us C, which will be 111 degrees, 44 minutes, and 30 seconds. Okay, let's make those 4s look like 4s. Okay, so there's our angle C. Now, we've taken care of that. So now we can go back and look and know that we have two sides, and now we have all three angles. Well, we have a side and three angles to choose from. A side and three angles. Okay, so step 2 is still kind of indiscriminate. I can pick how I want to attack this, but we're going to go after side B first. Okay, that's going to be the sine of B is equal to C and the sine of C. Okay, and if I play this out and manipulate the equation first before I put numbers in, I'm going to transform this into B is equal to C sine of B over the sine of C. So just like in the math world, it's always a good idea to do your algebraic manipulation first. Okay, so let's put some numbers into this one. So B will be equal to C, which is 243.69 feet, all times the sine of B, which was 32 degrees, 24 minutes, 30 seconds, divided by the sine of C, which we now know is 111 degrees, 44 minutes, 30 seconds. Okay, I'll put that all in parentheses because that all has to go together. Multiply times the distance, and when I get done, B is going to be equal to 140.93 feet. Okay, so that'll take care of what B is. Now we can do what's going to go on with A. Okay, and this will give us the coordinates of the triangle, basically. If we, or not the triangle, coordinates of where the buoy is. Right. All right. Next thing we need to do is what did I ask you up here in the problem statement? Location of the offshore point. Oh, okay. What I'm actually looking for is this. Let's put that in green. I am looking for this point on the X and Y axis of where that buoy is. So we need the X distance and we need the Y distance. So we really don't need to know the distance of A. What we're really interested in is where is this point here. So now what we have is inside this, we can go back to a right triangle in here because we just dropped a perpendicular line from C to the baseline. And now we have this interior angle here. We have this side B, and we know we have a 90-degree in there. So now we're going back to just a straight up sine and cosine values to find where X and Y are for this position. So what we're looking for here, just to make sure everybody knows, we're trying to figure out where X and Y are in this problem. Okay, so let's go do that math. The other bit is if I did need to know A, I could go find A sine of A equals C sine of C, or it could be A sine of A equals B sine of B. Okay, that wasn't what the problem asked us to do. Sorry, I should have paid attention to what I actually wrote up there earlier. Okay, but you could go find those points using that. But really what we're after right now is step 3 for this problem is find X and Y coordinates for the buoy's location. Okay, so now we're back to just plain old simple right triangle stuff, because the way I divided the oblique triangle into a right triangle, and I can use all this stuff over here. So here's the math, and I'll take you back up again in a minute, but we're going to do X is equal to B cosine of A, because that's the known angle we have. All right, and if you're not sure what we're doing, go back and take a look at this, but cosine of A is equal to adjacent over hypotenuse. Okay, and what we need to find is the distance along the x-axis, so that's going to be our adjacent side. So this will be the x-axis coordinate. Okay, all right, so let's plug the math in here. 140 0.93 degrees. Oops, that's not degrees, that's feet. That is feet, and that's a 3. Okay, and we're going to multiply that times cosine of the angle A, which is 35 degrees and 46 minutes and 0 seconds. Okay, and if you multiply that all out, we will get 114.35 feet. Okay, and then we can find y, because it's going to be b sine of a, and that will equal 140.93 feet times the sine of a, which is still a 35 degrees, 46 minutes, 0 seconds. And that'll give us a coordinate of 82.37. I think that's what that is. Feet. Okay. So our measurements, or not our measurements, our coordinate for x and y here, let's go back to green for a minute. X and y turns out to be, x is 114.35, comma 82.37, and that's where we'll find that buoy if we know an exact grid coordinate to plot it on. Okay, so this example uses the law of sines and then goes into right triangle trigonometry to solve for it, and it's a matter of dropping from C perpendicular to the baseline AB a 90-degree angle, where that B2, I guess we could call this another value here, A, B, C, D, D, where we add a D there, that AD and AC and CD form a triangle. Okay, cool. All right, next one will be the law of cosines. Sorry, I moved the mouse. All right. Law of cosines. This one's a wee bit more complicated, but nothing that's all that horrible. Okay, it's just more to remember. Okay, and this is going to come with, draw the triangle again just so we got it. And we're going to have a point up there, and we're going to be like so. And we're going to twist around here and do one like, get off there, like so. Okay, and this will be B, C, A, B, C for the sides. Okay, all right. Law of cosines, get out of there, is A squared equals B squared plus C squared minus 2BC times the cosine of A. Okay, and then B squared is equal to, draw my A's consistently if I'm going to do it, A squared plus C squared minus 2AC cosine of B And then c squared will be equal to a squared plus b squared minus 2ab cosine of c. Okay. So with that, we now have all of these, and we can use this when use when we have 3 sides are known. Option 2, 2 sides are, no, 2 sides and, forgot, 2 sides and included angle are known. Okay. All right. So let's do an example of this one, and then let's see how this is going to turn out here. All right. So if we set this up, oh yeah, this is going to be an example similar to what you're going to wind up doing in a few weeks for a lab. Okay, we got a triangle that looks like this. Actually, before I do that, I'm going to put some points in here. We're going to start here at A. We're going up, 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 up. Okay, and you know what? Let's do that after I put the line in, because this will make more sense. We're going to have a fence line, something that runs along the property here. And we're going to have a point along here that we're going to deal with. Okay. And then we have another line that's going to come all the way over this way, and it also has some fence posts in it. And so we got a weird intersection in here in the middle of this. Okay. Now, the bit we need to know is this. So we're going to label this point N. We're going to label this point M. And what we're going to do is we're going to come off, oh, I guess that's not where I'm putting the M. We're going to put the M right there where that intersects. And this will be M. And what I have is a 90-degree angle in there that we're going to play with later. Okay. All right. Here's what we got to find. I'll give you that first before I fill in some more details here. So we got a property line of a non-rectangular parcel. Parcel is just referring to the land. It's the piece of property. Okay. Parcel of land defined by fences. Okay, and we're going to need to find the angle at, not angles, angle at the corner, okay, to compute the area of the parcel. Okay, we're going to do this with just one corner of this, but we do the same thing on all the other corners if we got a weird shape, such as an oblique triangle. Okay, and I'm going to walk you through this because this is going to set up some things for the world to lay out how we're going to do this lab in the future here, so you'll know some of the things that go with it. So I'll do this in steps. Solution. Step 1. Set taping pin. That's your red and white pin. At points M and N. Okay? And these are arbitrary, which means randomly put along the fence line. Okay? But where the fence is, okay? 2, we're going to measure B equal to A and N, okay? And that's going to come out to be this number, 98.34 feet. So 98 point, let's do that where you can see it, 98.34 feet, okay? And then we're going to do C equal to point A to M, and that's going to be 154.68 feet, okay? And we're going to have A equal M and N, and we're going to find out that's 106.18 feet, okay? And before I get dumb in here on you, I'm going to take this back out. Sorry, I don't want to put that right triangle in there, okay? This is an oblique triangle in here. We're not dealing with the right triangle stuff, okay? So sorry that I drew that in there. All right, step 3. Okay. Use law of cosines to find angle A. Okay. Now, this is going to get, I'm going to do this with a bunch of abbreviations first, and hopefully it won't get too confusing, but just like with all good things. So, angle A is going to be equal to, well, not equal to, angle A going to A squared is equal to B squared plus C squared minus 2BC times the cosine of A. Okay. Now, put this in terms of the things that make sense with the numbers and letters we have up here. But, oh, and as long as I'm up here, I should do this. This is 154.68 feet, okay, going from A to M. All right, and we know this one is 106.18 feet, okay, because we measured that. So we use the tape to measure A to N, A to M, and then we went from M to N, or M to N to M, okay, so back and forth across there, okay. So, all right, so this is going to look like this, and you can substitute all these A's and stuff for a few things here. So we're going to do this. M N squared is what A is. B is A to N squared plus C, which is A to M squared minus 2 times A to M times A M, okay, and then we're going to do cosine A, okay. So just to drag that out and have some more fun with it there. Now, we could do this a little more drastically, but just to keep things sane. But remember, when you're in here, we're solving for cosine of A. So if we can get this by itself and get the rest of the equations over here on the left, that would make life just a little bit easier in the long run. Okay. And the ways to do that are, well, complicated if you put all the numbers in. Being careful, we can get this into this bit. Okay, we're going to go cosine of A is equal to, okay, A N squared plus A M squared minus M N squared, all divided by 2 times A N times A M. Okay. Now we can just plug numbers in. This is probably easier than well, easier to get this all sorted out first with the variables and then plug your numbers in. Trying to plug your numbers in and come up with it. So AN, we're 98.34 squared plus 154.68 squared minus the 106.18 squared, all divided by 2 times AN, which is 98.34, and AM, which is 154.68. Okay, so mistakes that can happen here are real simple. You forget to do the squares. Okay, you forget to move things in the order of operations, like 2bc cosine A is all multiplied. So 2bc can be divided out away from cosine A, but it's divided equally on both sides. B plus c squared has to be brought over, and no, where am I going here? We got to get A to the right and make that subtract from it. So it's those simple things of watching which way the orders of operation go, moving your variables around. Okay. Anyways, when we get done, we're going to find out that we have a number that's going to look like where'd it go? We're going to get a number that looks like this. Cosine A will be equal to a decimal point, 0.7337749, and you want to hold those figures out there. Okay. Now, fourth step to this thing is find value of A. All right, so that's going to mean A is equal to the arc cosine, or the inverse cosine, of 0.7337749, and A will be equal to 42.798. Can't read that number. Okay, hold on, guys. I got to get a calculator and redo this thing because I can't see that number. Alright, let's try this and see if we get this number sorted out. Bad notes, sorry. Go there. Point 7337749 equals, okay, 42.7983863, and I want to stop at 1, 2, 3, 4, 5, 6, 7. I'm going to stop there. Okay. Now, that gives us our angles in degrees as decimal, and I'm going to convert that to okay, what's the matter here? I got 42.798 8363 converted. I'm going to have 42 degrees, 47 minutes, 54.11 seconds. Okay, and we can round that up to 42 degrees, 47 minutes, 54 seconds. Okay. All right. So we use the law of cosines up here to find the sides, and then we got into converting things into this sexagesimal number. So go back over this because this is what you're going to wind up doing for lab. And I'm sorry I tried to bring a right triangle in there. I'm not supposed to. We got point A. We got two fence lines that run along this way and this way. You're going to put a surveying pin in there, put the other taping pin up here at N, some random point along that fence, and then one over here at M, somewhere along that fence. And none of these angles will be 90 degrees, so we don't have to worry about that because we're going to use all cosines. And we're going to measure from pin A to N. That gave us our 98.34. A to M, that gave us 154.68. And then we will go through the manipulation of the law of cosines to get ourselves down so we can get cosine A out so we can find that angle. And we can find that angle, and then we have our answer here. Okay. And that should take care of stuff on the law of cosines and sines. Still more we can do with this, but I'm going to take a pause here while I set up the next half of this video. Okay, so now we're going to go take a look at circles. Oops, back to black, please. All right, so circle has primary places we can do this in. Now let's see if I can get a nice circle drawn in here by hand. This is going to be horrible. I like the old system of doing this, but let's see here for a second. Can I get view, draw, and where's the shapes, and I want a circle here about here. Let's do this, like so. Okay, you move yourself down here for a bit, and I think we'll be good. Okay, so there's our circle, and we're going to draw a bunch of things through this. So literally we have a diameter that goes through here. Okay, and hopefully none of this is new to you. Somebody covered this in math for you once upon a time. Okay, we also have a radius. And I want to do that this way. Okay, and then we have another line we're going to put in here off this, and let's make it like so. Okay, and this will be an angle in here. We have a arc out here, which goes from here to there. Okay, we have a point here in the middle of this pie-shaped piece is called a sector. Okay. We have a angle, which will be called the central angle. Okay. And, oh yeah, I should have put this in here. So plus dot here, that's our center. Okay. Now the other one we have is this. This one's called a chord. Okay. And then all the way around the outside of this thing, that's our circumference. Okay. Those are the basic shapes of this. Okay. Diameter, let's put some definitions in here. So a diameter is usually labeled as D, and it's a straight line no, we're going to redo that. Straight line passing through the center, joining two points on the circumference. Okay, that's a diameter. A chord is a straight line Okay, so a chord is a straight line that connects 2 points without passing through the center, which is why I got it drawn over here in the picture the way I did. Okay. All right. A chord or radius is a, oh, and this one is a capital R, and it's a straight line from the center to the circumference. Okay. So we can pick any point on the outside edge of that and you can have a radius. Okay. All right. Now, we've been using the word circumference quite a bit here, so let's define that one. And that's the length of curve line that forms the circle. Okay, and we're going to be interested in that because it's going to be defined as pi d or 2 pi r. Okay. The math world likes pi r, the engineering world likes pi d. Okay. All right, next things we got to deal with here. Area of a circle. Equals pi d squared over 4 is equal to pi r squared. I don't like the way I wrote that. Let's try that again. R squared. Okay. Again, we like to do pi d squared over 4. Okay. And I described to you a sector and an arc. I'm going to write these down anyways, just to an arc is a portion of the line on the circumference between two radii. Let's do those capital letters. Okay, so plural of radius is radii. And if we want to know the math for that one, it's the length of an arc is equal to the circumference times the central angle divided by 360 degrees. Okay, so there's that one. All right, a sector is any portion of the area of a circle. A portion, let's make that look like a P portion of the circle. Okay, and it's going to be defined as this: area of arc equals okay. So the area of the arc, or this area of the sector, but the area of the arc is the outside edge, times the is equal to the area of the circle. So we take the whole pi d squared over 4 bit, and we use the central angle measurement divided by 360. So we get a proportional ratio set up here by using the central angle over 360. So finding the length of the arc, do the same thing, but that's what we're doing. We're setting up a proportion for this. Okay. So here's an example of these two, so it can be put out in your mind for a bit. So if we have a circle, I could have done better than that. Let's do it. We know how. And I want draw, I want shape, I want circle, like so. Come on over here. Okay, back to here. We're going to do the center, stop moving. The center is here. We're going out that way and out that way. Okay, so we're looking for this as our arc, and we're looking for this. Okay, so let me give you some data here. So R will be equal to 8, 53.56. Okay, that's an 8. Let's make it look like an 8. Pen's not having a good time with me today. We got an interior angle here. I'm going to bring it up here. So our central angle is 28 degrees 13 minutes. Okay, and we want to find the length of the arc, and we want to find the area of that sector. Okay, so we're going to find the arc based on this 2 pi r, and we want to do the central angle. Make that an L. I'm just getting carried away because I want to use the angle symbol there, so I have to write it all out. We're over 360 degrees, and then we're going to plug numbers in. So 2 pi. Oh, and I should go back and define pi for you here in a bit. I will. And our radius is 853.56 feet times our central angle, which is 28 degrees 13 minutes over 360 degrees. So there's our ratio to find out what that is. And when we get done, we will have 420.36 feet. Okay. Pi. I promised you pi, didn't I? I should have put pi up there earlier. So when we're using pi, so using pi, we want to do this. So this is the Greek letter for pi. If you're doing this by hand and not using a calculator to do it, we want to use 3.14. Come on, make that look like a 4. it gives us that 7 significant figures there to help us find all the minutes and seconds we need and things. Okay, so don't get too worried, but just follow along. Okay, the last bit of this one is now we need to know the area of that sector. Okay, and in order to find that, we're going to use pi r squared times the central angle again, all over 360. Okay. I should have done that up there too. Okay. And we're going to plug this one in. So now we got pi. And if you use your calculator, you don't have to put in the 7-digit number. But if you're doing it by hand, we want to use the same number so we always get the same answer. Okay, so we're putting that in. Now we're going to go and do 28 degrees 13 minutes over 360 degrees, and if we're all said and done with this, we're going to get a number that is 179,400 feet square. So that's the answer there, and that's the answer we got up there. Okay. So those are the two things we're looking for in that problem. Okay. There are times where we're going to need this. Nothing to get too worried about, but you might want to know it. Somewhere in your engineering career here, you'll need to use this stuff. Okay, cool. Well, that's the end of this video. We will see you guys.